Hi, this is for ECE 3300 Lab for the summer of 2021, and this is Lab 6, the 16-bit barrel shifter. So we first had to come up with a design that we could implement into Vivado. Um, so we know we have our barrel shifter right here. This is the main module. We know it's going to have a 16-bit input, but this barrel shifter is going to have the ability to rotate or shift, and it can go either left or right, depending on these two control signals right here. This barrel shifter will also have a 4-bit input that determines the amount of times the values are going to shift. So it's a 4-bit number, so it has a possibility of rotating 1 to 16 levels, which is right here. And then we have some peripheral circuitry that we need in order to figure out what's going on here. So we have our 7-segment display driver. This obviously takes the output, the 16-bit output from the barrel shifter, and we output it to our 7-segment display on the Nexus A7 board. So we have our off, the 7-segment displays that are off, which is the left 4 7-segment displays. Then we have our 4 that are on, and then we have the segment values, which we want on, and then the decimal point, which we don't use. And then we have a reset, just in case we want to reset the clock divider inside this 7-segment driver. And then we have our system 100 megahertz clock. And then another block that we had to implement was in a counter. So this counter would automatically up count the amount of levels that would be shifted in our barrel shifter. So for this, we have a signal called automatic and manual. So I called it auto man. This would determine if the counter would pass the value and automatically increment the level count in here, or if we would do a manual input with this 4-bit manual bypass value right here. And then we also have a control signal called load, which passes this manual input to the counter, whether it be in manual or automatic mode. So we have a bunch of control signals, but we only have 16 switches on our board. So we need to have a couple registers to store the data that we need. So we have reg1 right here, which is the modifier register. This would hold the manual bypass value at the 4 least significant bits of the switches on the development board. And then the 4 most significant switches would control the automatic, manual, load, then rotate shift, and then left right. And then we have this register over here, which is a 16-bit register, and this would just hold the values of all 16 switches, which would be the input to our barrel shifter. Next we have this control signal right here. This is to toggle between the registers. So when this push button is low, we're going to be modifying the values in the input for the barrel shifter. And then when it's high, we're going to be modifying the modifier values inside register 1 over here. I forgot to include it in this picture, but as well we have 2 more push buttons, each to reset these register values whenever the push button is pressed. So we could see up here what each register stores. The register 0, like I said, just MSB to LSB of the barrel shifter. And then we have automatic, manual on the 15th bit, load on the 14th for register 1, and then as relative to the switches right here. Then we have rotate shift on 13, left to right on 12, and then all the manual bypass on the 4 least significant bits of the switches. So now we're going to talk about the code.
So this is our code for lab 6 of our barrel shifter. And first I'm going to go over the top module that encapsulates all the modules we made, and then I'll explain each module and how it connects to each other. So this is our barrel shifter module, our top module. And here's our inputs. We have our clock, our toggle register, each of our register inputs, our switches, and then we have our output. which is a register LED to let us know which register we're accessing, our decimal point, our AN, and our A to G for our 7seg. And so in this case, we had to utilize an LED to indicate which register we want to access. So in our design, we used 2 registers, 0 and 1, to store data that we input for our switches because we only have a limited amount of switches. So we needed to separate where the data goes, basically. And so here are the wires that'll connect each module together. And so our first module that we instantiate is an n-bit register, and this is reg 0. And then we have another one called reg 1. So as you can see, if our enable button is active low, it'll access reg 0. If it's active high, it'll access reg 1. So these two just store our data. And next is our 4-bit counter, which determines our auto/manual functions. So this is our module for our 4-bit counter. So first we have our clock divider right here to basically change the 10 megahertz frequency down to about 0.75 hertz. And this counter also determines what to do with the output if the auto/manual switch changes and if there's a load. So if load equals to 1, it'll pass whatever is in the switch to the counter. Or if auto/manual is off, then it'll also set the output to the input. However, if the load is 0, it won't pass any values to the counter. Or if the auto/manual is 1, it'll increment the output. It'll increment the output. So basically for auto, we are utilizing the clock divider to automatically shift our input versus the manual, we indicate how many shifts we want. So we don't have to wait for the clock to shift it for us. The next module we have is our n-bit barrel. And so that will take in our registers, our mod register right here. Right here, you can see the output is mod register out, and that'll take in an input over here. And we can see that for the output of the 4-bit counter, it's called barrel level select. That determines how many levels we need to shift. And so that acts as a select for our n-bit barrel right here. And then we have the input and output. So going to that module right here, we can see it's parameterized. In this case, we want 16 bits. So we set size to 16. We have a rotate or shift input, our left or right. And then the select input basically tells us how many shifting levels we need. So to calculate that, it would be log base 2 of our size, which is 16. So that'll equal to 4 minus 1. So we have 4 bits. And we have our input from the switches and then our output, our shifted output. We have a temporary output right here set to reg. And then here's our always block. The sensitivity list is rotate or shift, left or right, our select, and our input. So in our block, we first set our reg to input, and we have some if statements right here to determine what functions we're using. So in this case, if rotate is 1, and if left or right is equal to 1, it'll rotate left. And we have a for loop right here. It'll go from 0 to whatever our shifting level is. And it'll set that register to these values right here. So it'll shift however many levels we need or whatever we input right here. And so it'll repeat the same for rotate right. However, for shifting, since we don't need to keep the values, we just shift with zeros. We can utilize the binary shift operator in Verilog. And so that is what we see right here. Again, our select is right here to indicate how many shifts we need. Okay, going back to our top module. And finally, we have our shifted output, and that'll go into our SSD driver, which is right here. And so this code was basically what we learned in lecture. So a lot of it's identical to what we learned. We have our clock reset, our inputs, our DP, AN off, which is to just keep the top 4 segments off. And then our AN on, which is the ones we use, and then our A to G. So we turn off whatever segments we don't use. And here's some internal variables that we utilize. Here's our 7-seg decoder, which is hex to 7-seg. Here's our clock divider to make sure our display works properly. Here's our digit select to select what number is to be outputted. Here's a multiplexer to distinguish which input goes to which output.
Hello Professor, this is the test bench and waveform explanation for Lab 6 for Group C, where we are making a barrel shifter. I'm going to be explaining the test bench and the waveform of the simulation. So here we are making the registers and wires for testing in our test bench, and then we instantiated the module and we included something called shift out. It's used to display the value of the output for the barrel shifter. And then here we started the 100 megahertz clock, and then we begin the testing. We set toggle to 0, which means that we are using register 0, and it will hold the barrel shifter's initial value input. And then the next 2 lines, reset register 0 and reset register 1, will reset both register 0 and register 1 to 0 if they're equal to 1. And then next we set the input to be 16 bits F0, F0. It is stored in register 0 since the toggle is equal to 0. Then next we set the toggle equals to 1, and here we are now using register 1, and we set the input to manual no load shift right with a manual bypass value of 10. So basically we're taking F0, F0 and manually shifting it 10 bits to the right, and F0, F0 shifted to the right by 10 bits will give us 003C. And then next we add delay, and then we set the reset register equal to 1. This will reset both register 0 and register 1 to 0. It's basically testing to see if the reset will actually work. And then we turn it off, so it's no longer resetting the values. And then we set toggle 0, or we set toggle to 0, which means we are now using register 0, and we set the input to F0, F0, and then we set the toggle bit back to 1 to have the modifier register hold this input value. So the input value is manual no load shift left with a bypass value of 0100, which is 4 in decimal. So this will manually shift F0, F0 to the left by 4 bits, and we should end up with 0F00. The next input will be manual mode no load rotate right with a bypass value of 1000, which is 8. And this will rotate F00 but 8 bits to the right, and we'll end up with F0 at the end. And then the next case, the input is set to manual mode, no load, rotate, left, and a manual bypass value of 1. We are manually rotating 1 bit to the left, and F0 rotate to the left by 1 bit is E1. And then here the input is set to automatic mode with no load and shifting right, and with a bypass value of 111 or 15. Since we are in automatic mode with no load, the bypass value does not really matter. It is automatically shifting 1 bit to the right, and it increments each time. So it will be shift 1 bit to the right, and then shift 2 bits to the right, and then shift 3 bits to the right, and so on and so on. Here, the next case is when we set the input to automatic mode. It loads a bypass value, and it shifts right with the bypass value being 0001, which is 1 in decimal. So it's shifting F0 to the right by 1 bit, and we should get set 0787. And lastly, the last case is where we set the input to be in manual mode with loading a bypass value, and shifts right with the bypass value being 0100, which is 4. So we're shifting to the right by 4 bits, and we should end up with 0F0F. This is the waveform for the simulation of the test bench. So here we can see that the input is the 16 bits, which is in manual mode, no load, shift right with a bypass value of 1010 or 10. So we are shifting right 10 bits. So F0 rotated or shifted right by 10 bits is 003C, which is what we expected. And then here we can, if we zoom in, we can see the reset, if it actually works. So here the reset is of both registers are set to 1, and we can see that the output is set to 0 because of the reset registers. And then once it's set back to low, we loaded it with F0 again, and then we had an input, the 16 bits, which is manual mode, no load, shift left with a bypass value of 0100, which is 4. So F0 rotated or shifted left by 4 bits is, if we zoom out, we can see that it changes to 0F00, which is what we expected. And then this input is manual mode, no load, rotate right with a bypass value of 1000, which is 8, and F0 rotated right by 8 bits is F0 again. So that works. And then this input value is manual mode, no load, rotate left with a bypass value of 0001, which is 1. We are rotating left by 1 bit, and as you can see here, F0 rotated left is E1, which is what we expected. And then here we are in automatic mode with no load, shifting right with a bypass value of 1111, which is 15, but that doesn't matter since we're in automatic mode. It will shift right by 1 bit, and then shift right again by 2 bits and 3 bits, and then so on and so on. So we can see here F0 is rotated or shifted right by 1 bit is 7878. By 2 bits is 3C, and then 3 bits is 1E, 4 bits 0F, and then so on and so on. And then here we're in automatic mode where we set the automatic mode. We're loading the bypass value, shifting right with the bypass value of 1 bit. So we are shifting right by 1 bit. So F0, F0, shifted right by 1 bit is 7878, which is what we wanted. And then for the last case, we're in manual mode, loading the bypass value, and we're shifting right with the bypass value of 0, 1, 0, 0, or 4. We're shifting right by 4 bits. So F0, F0, shifted 4 bits to the right is 0F, 0F. And that's it for the waveform. Thank you.
Okay, so this is going to be the demo for Lab 6. So right here we have the input of the barrel shifter, and we can see that by this LED right here. So if I were to toggle the switch, we can see that this is now in register 1, and now we're in register 0 again. And I can clear both of these registers. This would be clear for register 0, clear for register 1. Okay, so now I'm going to start passing in values to the input of the barrel shifter. So just for ease of use, I'm going to pass in F to this second MSD value right here on our 7-segment display. And now I'm going to toggle into register 1, and we're going to start changing values. So now we're in manual, no load, shift right, and I'm going to shift 4 bits, and or shift 4 places, and we could see here that F is now moved over 1. Okay, so now if we put on left, we should see F become over here, and now we can rotate right, and let's say we rotate 8, and we can see F all the way over here now. Let's do 12 just to see that it does go to the other side for rotate. Okay, and now let's rotate left, and let's, oh, here we go, it passed in the other value to the register. I accidentally let go of my finger. But we could see that F did move. Here, let me clear the other register. Okay, so I just cleared both registers again, and just to make sure. Okay, so now we're gonna put F right back where it was, and then we're gonna pass in the rotate left, and we're gonna rotate by 8. And we can see that F does move to the other side. I did let go of my finger again though, so I'm gonna need to reset the registers. Okay, and then now we're gonna see if our automatic works. So once again, I'm gonna put F into this value right here, and then I'm going to hold this to access register 1, and then we're gonna go to automatic, and we should start seeing it shift by itself. We can see that's happening, it's shifting right. Now we can do it where it shifts left, and then we can rotate left, and then we could rotate right as well. Okay, so we can see that that works. So now let's put both of these low. We're still in register 1, so I can load a value into the output, so let's say 3, and then I can make it automatic. And then if I hold this low, we can see that now it's starting to count up again, which means everything works properly.